Good afternoon. I thought I would make the last one too, because I did six. I was like, well, why don't I just do all of six? So here's 6.5, assessing normality. This one's all about graphs. So if graphs are hard for you, obviously try to let the computer be your friend. But basically, remember, normal, it's like a bell shape. We have to assess how normal things are. And I believe this is going to be using the computer the most. I haven't looked at it yet. I always try to look at it like through the videos so I get like the eyes of you guys as you're seeing it for the first time. So here we go. I'm going right for it. Share the screen. I'm jumping right into the textbook. Okay, so we're going to assessing normality. I know, craziness. And again, if I'm not making sense for you, you got people like organic chemistry tutor and things like that. Where am I? I'm here, here. So I'm going to be writing some notes in 6.5. We've flown through this. There's not too many left. So got hypothesis testing, chi-square, and probably some ANOVA stuff. But again, we're probably gonna make you a t-test video. Why? Because I think it'd be really useful. Oops, I just messed up the order. Look at that. What did I put up here by accident? Two. Here we go. Oops. Set two. Go. Nothing wants to go in order for me today. There we go. All right, so here's 6.5, assessing normality. Let's jump into the book and see what it says, right? I'm assuming I'm just going to be making graphs. So let me do this. Again, I appreciate the comments about like that these are useful and helpful and that the pacing is good. But if you want a different pacing, if you got questions about these, just reach out. Tell me how they can be better. Following chapters includes that method, sample data, construct a histogram to determine if it's bell-shaped, construct a normal quartile plot. All right, so I've never really done one of these normal quartile plots, so but I'm sure it's not gonna be too crazy. All right. When trying to determine a collection of data has a normal distribution, we can visually inspect the histogram to see if it's bell-shaped. And we can also do a normal quartile plot. I guess we did it before. I guess I just don't remember. So what is this normal quartile plot? What are we making today? A normal quartile plot or normal probability plot is a graph of points x and y where each x value is from the original set of the original sample data. The y value is from the z-score. Oh, that's cool. So all the x points are the same, but the y's are the z-score. We have done these before. That's cool. So what does it look like? Oops. I just have to move this. So normally, what do we got? For our histograms, we've got ranges down here. Then we have frequencies here. And as long as it looks generally like this, oops. As long as it looks generally like this, we can be like, oh, sweet, it looks normal, right? Ta-da, you can fold it, it'll be magical. Now, instead of having the frequency over here, we have the z-scores. We've got our z-scores over here. So we'll still have the same x values or ranges down here, but now we're just looking at the z-scores and we'll see if it's normal. That's pretty cool. The y values are the z-scores that is expected from the standard normal distribution. So procedure for determining whether it's reasonable to assume that sample data are from population having normal distribution. We've got the histogram. That's what this guy is. Histogram. And we've got this normal quantile plot, wild name. Apply the following criteria to determine whether distribution is normal. All right, so let's see. If the patterns of the points are, if the population distribution is is normal if the pattern resemble a straight line. The points do not show a systemic pattern. Does not form, so they do not fall in a straight line, and the points show some systematic that is not a straight line. Okay, got it. So for this, because it has to go from small to big, that makes sense. So these are our z-scores. Remember, the middle should still match in the middle. And so they should all kind of fall and be like kind of positively set up. And we should have kind of like a line that falls through it. That's pretty cool. In addition to using histograms and normal quantile plots or other more advanced procedures, such as the Ryan-Joyner test. Who are you, Ryan-Joyner? Okay. I was hoping to know who you were as a person. Ooh, okay, that's a bit. But let's just see who you are. We got no images of our friend Ryan Joyner. That's so sad. I'll see if I can find who this person is. Unless it's two people, unless one is Ryan and one is Joyner, you know? Other tests for normality include the Shapiro-Wilk test, the D'Agostino-Pearson test, the chi-squared goodness of fit test. I've used it. Okay, the Kolmogorov-Smirnov test, Lilliefors corrected chaos test, the Kramer test. I know about Kramer. Anderson-Darling test, Bloch-Barrett test, Anscombe-Glynn kurtosis test. Kurtosis I've used before, so you can look at some of these people, see how they came up with it, why they came up with it. I think that's really important. What if there were mathematicians at the end? And I go to search. All right, so there's Ryan. It's Barbara Falkenbach Ryan. Doesn't even have a picture. That's sad. Usually like to know where these people come from, but that's okay. Let's keep going. I'm always trying to show you why people come up with this stuff, but it's sometimes it's hard. Part two of this section, we will be describe the process of constructing a normal quantile plot, interpreting a normal quantile plot. So the first case shows the histogram, corresponding quantile creates a straight line. I love it. All right, so if it's a uniform, will be kind of curvy. I like it. So if we're all normal, we're going to get a curvy line. It doesn't fall straight. We're skewed. I think it's going to be kind of high on one side, low on the other. Let's find out together. Nice. See, really high on one side and lower on the other. I like it. So it's skewed to the right. We're not going to be falling along the lines. All right, let's make one. So the following is a relatively simple for manually constructing a normal quantile plot, and it's the same procedure used in StatDesk and this fancy graphing calculator. Some packages use various other approaches, but the interpretation of the graph is essentially the same. First, sort the data by arranging the values from lowest to highest with a sample size of n. Each value represents a proportion of one n of the sample. Using this known, find the values of 1 over 2n, 3 over 2n, 5 over 2n, okay? And so on until you get the n values. These values are cumulative areas to the left of the sample. Use a standard normal distribution software or table to get the z-score. So we need to get all the z-scores, match the original sorted data from their corresponding z-scores found in step 3, and then plot the points. Examine the plot. Damn. Okay. That's a lot. That's a whole lot. So let's do this by hand and see what we got. So Commute times and pending speed. Let's consider the sample, the first five. So here are our numbers. We got 20, 16, 25, 10, and 30. The first thing they wanted us to do is order this business. So that's what I'm going to do. We got 10, 16, 20, 25, and 30. Cool. 1, 2, 3, 4, 5. So my end is 5. All right, so each value represents 1/5 of the data. So we proceed to identify the cumulative areas left of the corresponding values. So these become specific areas. So if this means I've got 5, right? So if I have a pie of 5, I need 5 slices. If we have a rectangle of 5, we need 5 of these slices. And basically, these are going to give us the left areas expressed. So 1 over 2n, 3 over 2n, 5 over 2n. So this is going to be our 1 over 2n, 3 over 2n, 5 over 2n, 7 over 2n, and 9 over 2n. So these are all the areas to the left on the left side of it. So these are our values. What is our n? Our n is 5, right? Why do we have 5? Because we have 1, 2, 3, 4, 5 of these things. This is just the formula to get those 5 values. And you'll see if we add them all up, they should be to the left of what 5 is. So 1 over 2 times 5 is 10, so I have 1/10. 3 over 2 times 5 is 3/10. 5 over 2 times 5 is what? 5/10. 7 over 2 times 5 is 7/10. And 9 over 2 times 5 is what? 9/10. How does this work? Well, if we're to the left of some sort of value, right? And I want to know everything that's going on, but this thing is cut into 5 separate pieces. This is 1/10 of my data to the left of it. This is 3/10 of my data to the left of it. This is 5/10. This is 7/10. And this is 9/10 of my data. It's almost the whole thing. Everything is to the left. Why do we have these 5? It's because there's 5 data points. So we know we have 1/5. Each one has to represent 1/5 of the picture. So they're all going to be what? 1 out of 5 is 20, 40, 60, 80, 100. They're all basically going to be 20%, but we went to the left of that data, and that's how we get these values. All right, now we got to get the z-scores. Let's get them z-scores. So our z-score, our first one is going to be what? 10%. It should be what? The first one is, oh, sorry, we have to go backwards because we have the percentages and not the z-scores. So I need Excel equals normal dot inverse. And what do I need? I need 10%, 0, 1. See how the first one's negative 1.28? Negative 1.28. And then I'm just going to take these and I'm just going to change what the percentage. The next one's going to be 0.3. Next one's going to be 0.3. Next one's going to be what? 0.5. Point 0.5 should be 0. Nice. The other side should be exactly the same, but because we're on the positive side of the bell curve, it should change. So the next one should be 0.7. We know this should be positive one, positive 0.5. Nice. And the last one, with our 0.9 should be a positive 1.28. So here are values for the z-scores. And then we have to plot the points. That looks pretty. I'm sure we can do this with a, with the Desmos or whatever we want. I'm just plotting the points. The first one is our first value. Ah, okay. Our first value was 10 because the x's should be the same. And then it was a negative 1.28. Our next one was 16. Our next one's going to be 16. And I believe it was a negative 0.5. Our third one is 20. And this one's got to be our 0. Our fourth one is going to be 25. And it's going to be positive 0.5. And our last one's going to be 30. And it's going to be a positive 1.2. So these should be our dots. Let's see if they are. Yep, there are dots. They look like they're a straight line. They look like they're a straight line to me. So we can say it's normal. They zoomed it in, which is fine. I'm totally cool with that. We examine the normal quartile plots. The points do appear to lie reasonably close to straight lines. So we conclude it does appear to be normally distributed. Okay. Okay. That's kind of wild. There's got to be the way to just put this on a StatCrunch or something. Okay, so we're already at the end, right? Let's see if we can do this with StatCrunch. There's a QQ plot. Right. Let's make this QQ plot, and we'll also make a histogram too. Let's go into StatCrunch. What's our data? Our data was 10, 16, 20, 25, 30. 10, 16, 20, 25, and 30. And let's make a histogram real fast first. Here's our because there's one of each. Doesn't really help us. Unless I were to change this into frequencies. So let's do this QQ plot. Here's our QQ plot. All right. We have our first variable. I'm going to put that in. Select the desired data column and then just click compute. That's it. That's kind of wild. Here it is. Oh, that was so nice. That was fast. I like it. Does it do it on Excel? Okay, let's go to Excel. Let's see if I can make one of these QQs. Or a, whatever it's called. What is it? Normal quantile plot. Let's see if we can build one of these crazy things. All right. Let's see what we got. What's a graph? So I think I need to go to insert. Oh, it does the Pareto. That's nice for us. Fox and Whisker. Um, all right, let's find the actual name of this thing. It was a quantile. Doesn't have it. All right. So that's kind of annoying, but at least, oh, you have to do the add in. All right. Charts. Okay, so the add in I remember only worked when I was actually in this thing. Okay, so let me do a new one. Boom. All right, so I gotta go to data. Okay, it's not there. All right, so we gotta go to the Excel stat. Click on the Excel stat tab in the ribbon. Excel stat. Do I have Excel stat? There. XL. Oh, great. Isn't that fun? All right, well, that one's not being my friend. Sorry, I keep getting some text messages. Well, we're not going to use Excel. We're using StatCrunch. Sorry, it's just not being my friend. So let's jump into these. All right, before I jump into this, just give me a moment. Okay. Um, wait, we need the questions. All right, let's see what we have for these. Whatever ones are that we're facing. And this is the last one, which is nice. 4, 7, 9, 13, and 14. Okay. So we're starting with number 4. The accompanying histogram is constructed from the pulse rates of 153 men, including in this appendix B. And the requirement for an order, what you think to what you conclude about the population based on the histogram. For number 4, I'd probably say that this looks pretty normally distributed. Um, just based on the histogram, you can say it's slightly one way or the other, but I think we'd be able to assess normality. Um, If you plan to conduct further statistical tests and there's a requirement of normal, what do you conclude about? I think we can say this is normal. That's just me. If you want, please go deeper here. Really think about it more. I'm gonna do more like the hands-on ones. All right, here's 7. The normal quartile plot represents service times during the dinner hours of Dunkin' Donuts. This is not, the Dunkin' Donuts one is not. This one does not fall along the line. It is not normal. All right, where's 9? So in number 9, refer to the indicated sample data and determine whether it appeared to be from a population with a normal distribution. Assume that requirement is loose in the sense that population distribution need not be exactly normal, but it must be a distribution that is roughly Gaussian. All right, so we're gonna do the weight of M&Ms. Okay, let's make it happen. The weight of M&Ms. Cool. So, sorry. It's in Appendix B. Let's get this weight of M&Ms. Was it the candies one? All right, I think it's a different one. Data set 38. Yeah, it is this. Red, orange, blue, yellow, green. Let's insert one of these. All right, so the first thing I'd probably have to do is make a histogram out of this, which I'm not really wanting to do right now. And they're not all the same, these weights and eminence. So let's go into StatCrunch and mess with it. Because we're gonna have to do one of these Q1s anyway. So let's go to number 9. It's gonna be Appendix B in StatCrunch. Data set number 38. All right, so let's go to data. And let's do a QQ plot. I'm gonna take all of them. This is pretty close. These look pretty close to being around the line. I'd probably go with it. These are all 5, so definitely green, looking good. These are all, I believe, close enough to the line for me to say that this is. Now, how can we make sure these are roughly bell-shaped? Well, we can do a graph. And we can make a histogram. And we can do one for each of these columns. Let's see without doing this. Let's see what happens if I do it without. Sweet. So red is looking good. Orange is looking pretty good. Yellow's looking good. I don't know about brown, but blue is looking good. And green. So they're all looking pretty much like histograms. I'd put all these charts in. The only ones that I'm worried about, like if only one color seems off, the orange. And let's look at the oranges. The orange ones, QQ plot. And we can just pull them up again. Yeah, I would go with it. I think they're close enough to the line. That's just me. Everybody's different, but this was the one that was off. But yeah. You can say it's not true for one of them, but it's true for all the rest. All right, let's look at 13. Um, You generate a quartile plot, then determine whether the data is normally distributed. Cool. Well, we just did it. So this one's short. Just make sure you put all the graphs in and try to understand what they mean. You give me descriptions of them. I'm pretty sure you should be good to go. Good luck, and let me know if you have questions.